Hi everyone, this is Tianzheng. I'm happy here to present our work, Live Semantic 3D Perception for Immersive Augmented Reality. 3D perception is a fundamental task for AR or VR applications. In advanced AR/VR applications where users are able to interact with the real world, it is crucial that the system not only needs to know the 3D geometry of the scene, but also semantic information. Also, 3D semantic information is highly requested by robotics applications, as semantic perception can be used to perform complicated interaction with objects, as well as robust navigation tasks. However, although 3D geometry reconstruction has been widely studied, 3D semantic prediction is still in a relatively early stage. Existing methods are either not fast enough to process a room-scale large point cloud in real time, or not accurate enough for practical use. Also, the computational efficiency is what AR developers care a lot about. Portable devices usually have limited computational resources, which puts extra limitations on the system design. So we already achieved a highly efficient, dense 3D reconstruction system from our previous work, Flash Fusion. It has a fast loop detection module and a global optimization mechanism to ensure both performance and global consistency. So in this work, we proposed a new 3D semantic segmentation method, combined it with our 3D reconstruction system, resulting in a combined 3D geometry and semantic perception system. We further built an AR application based off that and showcased the use of our system in the immersive AR scenario. Before we dive into our method, let me briefly introduce some of the popular methods that enabled learning from 3D data. Since 3D data are so different from 2D images in the sense that they are sparse and they are disordered, which means that any permutation of a set of points represents the exact same point cloud. One of the solutions is PointNet and various networks that are based on it. So the fundamental idea of PointNet is that the network is designed to estimate a permutation invariant set function. PointNet uses a max pooling function to achieve that. So no matter what the order of the input, the max function always output the same value. So that solved the problem of disorderness. It is proven to be very useful in hierarchical structure to form a multi-layer network. PointNet is widely used because it has some good features. One is that it directly consumes point clouds, as point cloud is one of the most common representation for 3D data, and because most PointNet-based networks have relatively fewer parameters, it's usually fast to compute. However, PointNet cannot deal with very large point clouds, so you might have to split a large point cloud into some small blocks before processing it. So this is a problem because we always want to learn the global information as much as possible. Also, the model capacity limits the learning ability as well. Another popular solution is sparse convolutions. Just like 2D convolutions, 3D sparse convolution performs 3D convolution on voxels. As the dimension increases, the number of operations increases exponentially. So it is very important that we take the sparsity of 3D data into account. So in 3D sparse conv, only voxels that are not empty gets involved in the computation, so that we don't have to waste memory and computation on empty voxel grids. So compared to PointNet, sparse convolution enables larger and deeper networks, while it's not fast enough for real-time use yet. These are two popular sparse convolution frameworks. They are Semantic sparse convolution networks and the Minkowski engine. These are all great, but neither of them is able to be directly used in online prediction. This is where we start to optimize the sparse convolution to make it faster. This is an illustration for a single sparse convolution operation. This happens in a GPU CUDA kernel. Since 3D voxels are disordered, spatially close voxels may be scattered in the GPU global memory. So every CUDA kernel needs to retrieve the input from all over the place. They're not necessarily connected. So this forms a very inefficient random access of GPU global memory. This does not happen in 2D because in 2D they are all structured and continuously stored in the memory. So this is a major performance bottleneck here. In order to tackle this problem, our solution is to group spatially close data points into small chunks. It is based on the observation that each input location is accessed multiple times when generating different output features in its neighbor. Therefore, by splitting the input space into independent chunks, voxels inside each chunk have a high probability of using the same input features for convolution. These input features within a chunk can be cached in the shared memory, which has higher bandwidth by 2 orders of magnitude than the global memory. Now, those uncoalesced random global memory access only happens once. The rest of the time, the CUDA kernel just needs to retrieve the input features in a high-speed cache. So here are more details. This figure shows the sparse convolution of a single chunk. Since all chunks are processed in parallel independently, we just take out a single chunk here, for example. As you can see, there are n input and output features in this chunk, each with some channels of features. Here C in channels, here C out channels. We divide those channels by a number, let's say B. Each CUDA kernel generates B output channels in parallel, like it's boxed in green here. Inside each chunk, there are threads running in parallel, dealing with B input channels at a time. Then iterate over all input channels. So you can see in each channel, these marked out parts of input and weights are cached in the shared memory and are shared by multiple threads. Considering that point clouds are usually unevenly distributed and sampled, it is also important to make sure that each chunk has roughly the same number of data points. We accomplish this by adaptive chunk splitting. We divide chunks in a 3-level manner, each subdividing chunks that contain too many points into smaller chunks. This results in chunks that have similar number of points, so that when different GPU CUDA blocks are assigned to process different chunks, they will have a balanced load. Moving on to our network design. We adopted the popular UNet structure and modified it using the cross-scale fusion module. A common UNet structure consists of a pair of mirrored encoder and decoder. They downsample the input a couple of times first and then upsample it to the original scale. Instead of direct upsampling, we use fusion modules to incorporate features of different scales. It's essentially a spatial attention mechanism, making the network able to learn how to use multi-scale information. This is a single fusion path from the scale j to I-1. The output of the jth level decoder is multiplied by a and b to learnable parameters and get element product, and then upsampled and added to the I-1 scale feature. Each fusion module contains multiple fusion paths coming from all lower scale levels. Here we show some evaluations. Firstly, compared to the Minkowski engine and the original sparse CompNet, our method is way faster than them. And compared to the original sparse convolution, our method also gets a great acceleration in terms of inference time, especially when dealing with very large point clouds. So here, the inference time increases very slowly when the number of points increases. We also achieved the state-of-the-art accuracy on the S3DIS public dataset, outperforming all existing methods. Our demo further shows the use of such online 3D perception system. Since we know the semantic labels for 3D surfaces, we are able to know the material properties of them, which can benefit AR experience. For example, when a virtual ball hits a table and a couch, the rebounds should be significantly different as the couch is much softer, making the rebounds weaker. And now we are showing the online 3D semantic prediction results. So all clips are shooted on a portable device, which is a Surface Book in our experiment. Now we're showing the geometry reconstructed and color the geometry. Now the semantic label. And now we're showing the table and couch example that I mentioned before. So here is with the material properties. You can see that the virtual ball bounced weaker on the sofa than on the table. But if we turn off the material, then the balls will get bounced to the same height, which is very not unrealistic. Here are more examples of such experience. In the end, we want to introduce a little bit of our follow-up work. In this work, we came up with a novel 3D semantic instance segmentation method that uses the similar sparse convolution network. This one is also able to run online on a portable device. It reached the top on both ScanNet semantic and instance segmentation benchmark. You are welcome to visit our website for more information. Thanks for your attention.